As we go through our training, we learn a large number of equations. And just remember your structural courses and the moment and shear on beams and simply supported cantilever, and in hydraulics and in geomechanics. However, everything goes back to the basics. And so I would like to review the basics with you because we cannot afford to forget it. And so the fundamental laws of nature, we have to go back to our physics books. And we're going to start with Newtonian mechanics. And the first one tells us the concept of inertia. And that is that a body will tend to remain either static or under a steady state velocity unless you do something to it. The second law is that force is equal to mass times acceleration. If we want to move a mass, we need an unbalanced force. And that goes all the way down to the settlement of soils. If soils settle, it's because grains move, and if grains move, it's because they have an unbalanced force that is causing their motion, their acceleration. The first one says that for every action, there is an equal and opposite reaction. And we recognize that in every aspect of geotechnical engineering. When we do the analysis of slope stability and we take a slice, then we have that the weight and all the other forces acting on it are going to respond to the fact that for every action there is an equal and opposite reaction. Notice that I have not listed the fact that the other one, the other Coulomb's law, which says that the force between two masses is inversely proportional to the distance between them square times a universal constant capital G. Now, this has important implications. For example, if one of the masses is the Earth, and I stand here and I feel my weight, by combining these two, I can conclude that all this component is little g. So when I say that my weight is equal to my mass times gravitational acceleration, that is the interaction of my mass with the mass of the Earth. And notice that it's inversely proportional to the distance, and now you can do important implications. For example, this is 6,400 kilometers, and the space shuttle is flying at about, let's say, 200 kilometers. So nothing here is to scale, but now you can compute the acceleration on the space shuttle, and in fact, it's not zero gravity. It's feeling probably 90% of gravity. So we need to understand actually what is going on in the space shuttle. But before I go any further, and I confuse with so many details, there are three Newtonian mechanic laws: inertia, force equal mass times acceleration, which is at the essence of all dynamics. This is where we start the derivation of the wave propagation equation for acoustic and mechanical waves, and that for every action there is an equal and opposite reaction. Newton's law for masses is not one of the fundamental laws, but we use it extensively, so let me list it as part of this summary. The second one is electromagnetics. If we start with a static charge and I fly around it and I measure the flux of the electric field, imagine that I fly with a space shuttle around the Earth, measuring the flux of the electric field, and then I integrate the flux of the electric field around the surface that I'm flying through, and these are vectorial notation, this is going to be equal to the charge enclosed in this body that I have flown around. If I do the same for a magnet, now it gets tricky because a magnet has both the positive and the negative, and so when I fly around a magnet, the integral of the magnetic field fluxing out of this surface is going to be equal to 0 because I have both the positive and the negative, and I cannot separate them. These two are called Gauss's law, Gauss' law of electrostatics and of magnetic fields. Then came Faraday, and Faraday was an experimentalist working with magnets, and he noticed that by moving a magnet through a coil, he could measure a charge on the ammeter connected to the coil. Now, he was scratching his head because he said the static charges inside the coil shouldn't move when I move a magnet. Therefore, he concluded that the time-varying magnetic field must produce an electric field. So the time-varying magnetic field creates an electric field that causes the charge movement. On the other hand, Ampere noticed that if he had a current going through a cable, there was a magnetic field producing the cable. And then came Maxwell and said, you know, nature is symmetric. So I should also be able to produce a magnetic field by a time-varying electric field. And so this is the Ampere-Maxwell equation. But Maxwell went further. He put all these equations in the mathematical blender, and he predicted the wave equation. And therefore, he concluded that electricity and magnetism are totally coupled, and that is electromagnetic phenomena, which was not proven until Hertz actually proved it 20, 30 years later, that electromagnetic waves actually exist. And that was such an important and time-changing concept that still today, when we talk about frequency in the electromagnetic spectrum or in any dynamic system, we talk about Hertz as the measure of frequency. Now, then there are a couple of other laws that are guiding us and constraining us tremendously, and that they come from thermodynamics. The first law tells us that energy is conserved. We use that one, for example, in pile driver analysis. We assume that all the energy that we deliver with the weight of the piston gets transferred onto the pile, and that is the energy that gets consumed in penetrating the pile into the subsurface. The second one is also equally important, so this is the first law of thermodynamics. The second one tells us that processes occur in one direction only. And so this is the idea that disorder is always increasing, or entropy increases, or that every process is irreversible unless you inject energy into it. And you may wonder why that law. The origin of that law is because imagine that I hammer a nail into a wall. I am conserving energy, but all the energy, which was kinetic energy from the hammer that went into the nail, as the nail penetrates, it broke bonds and created lots of thermal activity and thermal energy, and thermal energy is random. So if thermal energy, all the molecules could get organized and say, come on folks, let's push the nail out, the nail would come out. But that's the essence of the second law, is the randomness of thermal energy. So processes are irreversible. Now imagine, for example, that has implications to everything we do. They only occur in one direction. And so when you hear nowadays people promoting circular carbon economy, well, you know that that is thermodynamically impossible. So we can capture the carbon that we emit, but it will cost tremendous amount of energy to do so. So far, we have 3 Newtonian laws, 4 electromagnetics, 2 thermodynamics, Newton, Maxwell, and here thermodynamics. And now there are some very important conservation principles. First, we conserve energy. And these are equal, so we are not going to count them. The second principle is that we conserve momentum. And that is both linear and angular. Once again, the case of pile driver, and in angular momentum is for machine foundations. For example, we would be calling on angular momentum. The second conservation is 1, 2, 3. The fourth conservation is the conservation of charge. So if we started with so many atoms and charges in general, electrons and protons, a process will conserve charge. And for example, if you think of biomediated processes, the bacteria will lower the activation energy for certain reactions, but will not invent charges that you didn't have in the system. And finally, conservation of mass. We use charge conservation a lot when we analyze double layers, electrophoresis, electrical conductivity in soils. If we want to understand diffusion in depth, we call on charge conservation. More frequently, though, for the classical geotech, we use mass conservation a lot. This is the starting point, for example, for Laplace's equation for seepage. All the Q in, all the flow in must be equal to the flow out. That leads to Laplace's equation. Or in the case of consolidation, Terzaghi's one-dimensional consolidation, there is flow coming in, the element is contracting, so there is a change in volume per unit of time, and there is a fluid that goes out that will conserve the mass between the flow that went in and the flow that is being squeezed out of the soil. So here we have 5 conservation principles, but we're going to account for the fact that energy is the same as the other one, so it's 5 minus 1. So we have 4. Folks, this is all we need. This is all we need to analyze all our problems. This is the starting point for all our problems. So many of our problems start from equilibrium. And so F equal ma, or the sum of the forces equal to 0, the sum of the moments equal to 0, all that is equilibrium, is Newtonian mechanics. Many of our problems start by mass conservation, conservation principles. Everything that we do in geophysics comes in ground penetrating radar, time domain reflectometry. You need to understand electrical resistivity and electrical resistivity tomography. It's all written here in Maxwell's equations. There is one more guiding concept which we are not going to count, but there are some guidance. And for example, one of them is the concept of simplicity. For example, Occam's razor criterion. If there are 2 theoretical concepts, one is very complex, the other one is simple, in general, bet on the simpler one. And we can say the same about complex constitutive models, for example. bet on the simpler ones being more robust. The other one is the concept of beauty. But the problem is, what is beauty? And like we said, beauty is in the eye of the beholder, but there are some equations that are just beautiful. F equal ma, or E equal mc squared in Einstein's relativity. They're just simply beautiful. But then there is one more that I would like to bring your attention to, which is Le Chatelier. And Le Chatelier's principle says the following: and nature will do everything it can to oppose change. So if you're trying to freeze water, nature will say, you have to give me lots of energy because I'm going to pump energy to oppose change. And so the latent heat for phase transformation, the heat for phase transformation has the direction of opposing change, and the same for evaporation. So in case you have doubts as to the direction of a process, always think that nature will try to oppose change as much as it can, and that is Le Chatelier's principle. We are not going to count them, but keep them in mind: Occam's criterion, Le Chatelier's principle, but above all, we have 13 important laws that are the foundation of everything we do in geotechnical engineering.